They're called natural gas liquids, or NGLs for short. And you've probably heard of some of these, right? Ethane is a huge deal. It's the main ingredient for the global plastics industry. And of course, propane and butane. Many of us use those for grilling or in lighters. These are all heavier hydrocarbons just mixed in, waiting to be pulled out.
And that's really the whole puzzle. These NGLs are absolutely critical raw materials for modern life, but to use them, you've got to get them out of that main natural gas stream first. So, how is it done? Let's get into the engineering behind it.
Okay, we'll start with one of the most established techniques out there, the absorption method. Honestly, the best way to think about this is to imagine using a special kind of chemical sponge, a sponge designed to soak up only the NGLs and leave the natural gas behind.
So here's how that sponge works. First, the raw or wet gas flows into a big, tall tower. Inside, it gets mixed with a special absorbing oil. This oil naturally attracts NGLs, so it literally just pulls them right out of the gas. Then, once that oil is full of NGLs, it gets heated up, which boils the liquids back out so they can be collected. Pretty straightforward.
Now, the industry uses some simple but really important terms here. The oil is called lean oil when it goes into the tower, all clean and ready to work. After it's done its job and soaked up all the NGLs, it's called rich oil. It's a really simple way to track how the process is working.
And you can see, basic absorption works pretty well for the heavier liquids. It gets most of the butanes and pentanes. But look at propane. To get really high recovery rates, over 90%, you have to add refrigeration. This brings us to a second major method, mechanical refrigeration. Instead of just relying on the oil, this process uses a massive, powerful refrigeration system, kind of like a giant air conditioner, to pre-chill the lean oil. Colder oil is a way better sponge, letting it grab more of those lighter NGLs. But even that has its limits, especially if you're trying to get something like ethane.
So to get even colder and capture even more, we can turn to a totally different principle, a really clever bit of physics. Instead of chilling a chemical sponge, what if you could make the gas chill itself just by playing with its pressure? Well, that's the whole idea behind the Joule-Thomson effect. This right here is a low-temperature separator system, and it's a perfect example of this effect in action. Just follow the path of the wet gas feed. It comes in, goes through a heat exchanger, and then it heads toward one very, very important little component.
And there it is, the Joule-Thomson valve. This is where the magic happens. The high-pressure gas is forced through this valve, and its pressure just plummets. That super fast expansion makes the gas instantly get incredibly cold. So cold that the NGLs literally condense into a liquid condensate, which can then be easily separated out.
So absorption is a great workhorse, and the JT valve is really clever. But if you want the highest possible recovery rates, especially for that super valuable ethane, the industry turns to the absolute pinnacle of this technology, the turbo expander.
So the big question becomes, how do you take this idea of cooling by expansion and just push it to the absolute limit? How do you get the gas so incredibly cold that even the lightest NGLs have no choice but to drop out as a liquid?
The answer is with some seriously extreme cold. A turbo expander plant drops the temperature of the gas stream all the way down to around minus 49 degrees Celsius. That is unbelievably cold. And at that temperature, things start to happen that just aren't possible with the other methods.
And the result of that deep freeze? Just look at this efficiency. This process lets you recover 90 to 95% of all the ethane in the gas stream. That is a massive leap in performance, and it's what makes extracting this NGL so economical.
So how on earth does it do that? Well, this brilliantly illustrates how it gets that incredible performance. The turbo expander is basically the ultimate hybrid, combining the principles we've just looked at. First, the gas is pre-chilled using external refrigeration, just like in the mechanical refrigeration method. Then, that already cold gas gets expanded through a high-speed turbine. Think of it as a supercharged version of the Joule-Thomson effect. It's this 1-2 punch that creates that massive temperature drop, liquefying the ethane while the methane stays as a gas.
But what makes this process truly genius is its energy efficiency. See, the turbine doesn't just expand the gas, it actually harnesses that energy. As the turbine spins, it provides power to help recompress the leftover methane gas so it can be sent to the pipeline. It's this really elegant, closed loop that recycles energy and drastically cuts down on the plant's operating costs.
So, we've seen some pretty impressive engineering, but let's connect this back to the real world. Why does mastering this stuff actually matter to us?
Well, once that mixed stream of NGLs is pulled out, the journey's not quite over.
It's sent to what's called a fractionation facility, like the one you see here. Inside these big towers, the mixed NGLs are carefully heated and distilled, which separates them based on their different boiling points. This process gives you pure streams of ethane, propane, butane, and all the rest, ready to be sold and used.
Ultimately, it's a huge win-win. By taking out these heavier hydrocarbons, we get a cleaner, purer natural gas that meets the specs for consumer pipelines. And at the exact same time, we capture all those valuable NGLs that are the building blocks for the plastics, chemicals, and fuels our world really depends on.
From a simple oil sponge all the way to high-speed cryogenic turbines, the science of NGL separation has become incredibly sophisticated. It really leaves you wondering, though, as our energy needs and our technologies keep changing, what kind of new innovations are going to shape the next generation of gas processing?